So first I want to just introduce myself. My name's Dr. Christina Sweeney Hillesheim. Just to give you a little background for those of you that don't know me or didn't attend the first talk, I have a doctorate in chemistry and I have a master's of divinity in apologetics. And so my specialty or my forte, I guess, is the beginning of the universe creation. That's kind of the area that I am more interested in, and specifically looking at that for both a scientific and a religious, specifically Christian perspective, and seeing the relationship between the two. So today's talk is the second of my talks on science and religion, and this one is on the Big Bang Theory. So how did the universe begin? That is the question that the Big Bang Theory is trying to answer. So I just want to go through a little bit of the history of how the Big Bang Theory kind of evolved and where it ended up, and what do scientists believe, what did scientists believe, and what do they believe now regarding just this specific topic. So all the way up to about the early 1900s, most scientists believed that the universe really had always existed. It was eternal, it had always been there. It was pretty much the same now and then. It really hadn't changed. It was static, meaning it wasn't moving, expanding, or changing, and it was just infinitely big. So this big, infinitely always existing thing. The conventional view for most scientists up to this point was there was no beginning because the universe had always existed. Nothing really exciting had ever happened in the history of the universe. It was always just kind of there. So this was kind of the belief of the universe up until the early 1900s. But then in the late 1920s, Edwin Hubble, seen in the picture on the bottom left here, an American astronomer, was doing some measurements using the Mount Wilson telescope, which is seen, the observatory is seen on the top right, and then you can see the telescope itself. And this is located outside of Los Angeles, California. And at this time, this was the most powerful telescope. So this was the best thing you got in the late 1920s. And so as he was kind of making his observations, what he noticed was that the galaxies that are around us were moving away. And what he noticed was the galaxies that were near us, compared to the galaxies moving that were further away, they didn't move at the same pace. So the galaxies that were farther away from us, they would move faster and faster. So the further away from us you got, the faster these galaxies were moving away from us. So that might be a little hard to kind of grasp what that meant, but the idea of what that meant is kind of, it can kind of be illustrated in this example of this balloon. So if you think about a balloon, I would demonstrate it, but I actually am really bad at blowing up balloons. So you're just gonna have to imagine me blowing up a balloon, or look at this lovely young lady blowing up this balloon. And imagine each star here as representing either a particle or a galaxy. And so at the very beginning, when you have the balloon, the universe starts out really, really small, but then it's going to expand. And so as we blow up the balloon, the universe is expanding. Every one of these little stars or galaxies is going to move away from every other star or galaxy. And there's no real center of the expansion. Everyone is moving away from everyone else. So you can see that here, that like in the picture, the orange star is moving away from the yellow star and the blue star. And you can't even see this little green star because it's right here at the top. So everybody is moving away from each other in all directions. Is this expansion? And so this is kind of this idea of what this expansion was that Hubble was kind of noticing. But this was noticed, but it wasn't really completely understood at this time. And so they started to try to figure out, well, what does that mean? What does these observations mean? What are the implications of these findings from Hubble? So the first thing is, well, if the universe and if these galaxies are, expanding and moving further away from each other, then it means that the universe is not static. It's actually moving, it's expanding. So that kind of changed that original thought that the universe is eternal and that it's static. It's always this just big constant thing. So that's the first implication of his findings. It's not static anymore, it's expanding. And we can trace the progress of this expansion. If we knew where we're at now, like if we know where our stars on our balloon are, then we can almost work backwards in time to kind of figure out where they started at. And so what that means, if we worked backwards, is that the early universe had to have started off very small, infinitesimally small, very, very small. And then it expanded out. So that also limits the fact that we thought the universe was static and that we thought it was just really big and always existing. So the conclusion from Hubble's findings was, well, the universe may have had a beginning or been created. But even though this was kind of the implications of Hubble's findings, it was kind of ignored by scientists at the time, mainly because they weren't really sure, well, how do we determine if that's true or not? How can we test that? It just seemed, based on their technology at the time and their understanding of the universe, just a difficult problem. So people kind of just let it go and looked at other things. Until around after World War II, George Gamow had a group of nuclear physicists. He was an exiled Russian nuclear physicist, and they were kind of starting to investigate a little bit more about kind of the beginning of this universe. What would have this look like? And just kind of a side interesting note about George Gamow, it is believed that even though he was very imaginative, he had some really great ideas, he never in his life actually got a calculation correct. So I find that kind of funny. Little tidbit there for you, that you can be a well-known nuclear physicist and maybe not be the best at your mathematical abilities, but still make an impact. So keep that in mind for any of you watching this video who might be interested in science or math, but might not be the best at math. Or maybe he got it right and it's just a underlining joke that has happened through the years. Who knows? But back to George. So him and his little group of researchers, they believe that the early universe would have been very hot. So hot, similar to the idea of an exploding atomic bomb, as you can see in my picture. And as the universe expanded, as this energy would expand, it would cool. And as it was cooling, it would create the basic elements of nature, hydrogen and helium. But as he kind of had this idea, it wasn't really taken very seriously. And a lot of his opponents to his theory, they're the ones that named it the Big Bang Theory. And it's thought that Fred Hoyle is the one that kind of said it and dubbed it that actual official name, because George thought it was a bang, kind of like the bang from an atomic bomb. In addition, what else George Gamow thought and claimed, that if this were the case, if this was this hot Big Bang, that some pieces of evidence, some remnants of this Big Bang would still exist today. We would be able to see some things that were left behind. And what he said is those pieces that we would see would be in the form of microwave radiation. Now, when you think of microwave radiation or radiation, you might think, ooh, that seems really dangerous if that was still around, but it wasn't very strong. It would be all around us, but it would be weak. And when I say like microwave radiation weak, you could think about it like it wouldn't be enough to like defrost a pizza or anything like that. Very, very minute. But it would be strong enough that we could detect it. But at that time, no one thought that we would be able to. So George said it would be strong enough to be able to be found, but we didn't really have the equipment or the capabilities at that time to detect this. So yet again, theory was kind of ignored as a good idea, but we can't really test it, so we're just going to move on. Now, most scientists were opposed to the idea of the universe having a beginning, because if the universe had a beginning, then we have to have some explanation for that. And at that time, we had some theories, such as George Gamow's theory, but there wasn't enough evidence to support it. It was a theory, but there was no physical or observations that were able to be made at that time to really support it. So instead of going and trying to find that information, find evidence to support the theory that the universe had a beginning, instead, what scientists decided to do is they said, okay, let's find some alternative. What are some alternative explanations for the evidence that was found through Hubble and his observations? Because at the time, if it had a beginning, the explanation was a religious explanation, that God was the creator. And most of the scientists at the time did not feel comfortable with that explanation. So there are some alternatives, and one of the alternatives that became very popular in the early 1960s was this oscillating universe, or that the universe bounced. So the idea was that the universe would be one size, be small, then it would get big, then when it gets small again, then it would get big. So it would do this kind of oscillating or bouncing kind of idea, getting smaller and bigger. Because of the observations of those stars on that balloon expanding, because the universe is expanding, this would kind of explain the expansion. And that when Hubble's observations were made, it was in the expansion state, the universe was, and it hadn't gone back to the decreasing state. And so this was the explanation that was produced, a theory as to helping to understand why the universe was doing the expansion. Well, Stephen Hawking, I'm sure you're aware of, he was currently studying in Cambridge at this time, and he thought, you know what, I think I can tackle this issue. Can I determine if the universe is really doing this little kind of expanding, oscillating, bouncing idea? And so this is what Stephen Hawking decided to tackle for his PhD thesis. And so through his studies and through his analysis, he determined that the universe could not bounce, that the universe had to have existed from a singularity. So the universe couldn't have always existed. It had to have a beginning via the Big Bang. I apologize. And so the universe couldn't bounce. So this theory that was produced was disproven. So then, okay, we're back to universe is expanding. It didn't always exist. It had a beginning, but we still don't really understand a lot about that. And we still don't actually have any physical evidence or observational evidence. So then in 1965, Arno Penzias and Robert Wilson, also American radio astronomers, they were testing a radio receiver, you can see in the background picture here, that was built for microwave communication signals. And as they were kind of testing this, they detected an unknown source of noise. Now, this was a complete accident, and they couldn't really figure out what this noise was. There's this noise, they weren't sure. These two gentlemen were not interested in cosmology. They were not interested in the Big Bang, so they weren't really looking for that. They also were not aware of Gamow's prediction. So with Gamow's work, he predicted that this noise would be, you would be able to find it because of that microwave radiation that he said. But they didn't know about it. So they pick this up. They're not sure what's this noise. They go in, they're trying to fix the joints. They're trying to clean things. There was actually a lot of pigeons around. So they thought maybe the pigeons, had like pooped or made a mess, or they were causing it. So they removed all the pigeons. Some people say they killed all the pigeons. But they tried to do everything they could do to try to remove this noise, and they just couldn't remove it. They couldn't get rid of it. And so what's said is, by chance, one of them were just happening to have a conversation with a cosmologist, and we're just talking about, this struggle that they're having with this background noise, couldn't figure out what it was. And this cosmologist is like, wait, I think I know what it is. I think this is the noise that Gamow predicted in 1945. So then cosmologist works with Arno and Robert to try to figure out and determine if it is this radiation that is producing this noise. And it was. So now we discovered that microwave radiation. And this ends up being one of the most important discoveries in the history of science. Because before, when it came to the understanding of the beginning of the universe, it was all kind of theories, but we didn't have any observational data other than Hubble's expansion that made that first jump, to have another big jump in the process of understanding just the history of the universe. And so this really kind of moved things forward. So what was it? How is it that the universe was created? What was the thought behind the Big Bang at this time? So the way that it's thought of is that first it started with a Big Bang. The universe had zero size and was infinitely hot. So boom, we have the bang, infinitely hot, lots of energy, and then it's going to start expanding. So boom, and then the expansion. As the universe is expanding, its temperature is going to drop. As the temperature is dropping, this is what's going to cause galaxies to form in some areas. And within the galaxies, we'll have smaller clouds of hydrogen and helium gas. And when the hydrogen and helium gas collapses, they are going to form the first stars. So now we have galaxies, we have stars that are starting to be produced from the expansion of the universe and the decrease in this temperature. Then what happens is that as these stars are created and as they start to burn up and use their fuel, when the star kind of dies, when it explodes, which is called a supernova, then the star itself is going to throw out new elements like oxygen and carbon into space. So now we have the formation of stars. When the stars burn up their fuel, now we have new elements that are into space, and these new elements, the dust, as we would say, from the stars, are what ends up forming the planets. So at this point, around 1970, the 1970s, pretty much nearly all the scientists agreed that the universe must have originated in the Big Bang. So now you can see the shift. Before, everyone thought that the universe was static and eternal. And now we have, okay, universe had a singularity moment. It started in the Big Bang. But what triggered the Big Bang? This was the next question. What caused that to start? What caused something that was infinitely small now to go boom and expand into this vast universe that we have, and to then create stars and planets and etc. So that was our next big question. So in 1979, Alan Guth, an American physicist, wanted to try to figure out this question. And so he was able to figure out what is called cosmic inflation. And so just like Hubble observed that the universe is expanding, he wanted to kind of figure out what was that expansion, mathematically, the speed, the rate of that expansion. And so he figured out that the universe expanded at a faster and faster pace, at an accelerating pace. So in a fraction of a second, the universe would have expanded to 1 trillion times its size, so 3 trillions. So within just a second, it expanded at a very, very fast pace. But what does that actually mean? And how did that happen? Why would it all of a sudden just start to expand at this really, really fast pace? What was the trigger for that? And so what Guth thought was that there exist two different types of matter. And so exists ordinary matter and self-repelling matter. So ordinary matter is, if you have an ordinary piece of matter, ordinary matter will attract other matter through the force of gravity. So the way you can think about ordinary matter is if I have an apple and I have the ground, the apple is going to fall towards the ground. So the apple and the ground are going to be ordinary matter. They're going to be attracted to each other through the force of gravity. Now, if either one of these, if the apple or the ground were self-repelling matter, then it would behave the complete opposite. Instead of the apple falling to the ground, now it's going to float away into space. So what Guth proposed is that the universe, the entire universe at the very beginning, was filled with this self-repelling matter. And so all of this matter was pushing against everything else. And so this would account for that sudden expansion of the universe, because this matter doesn't want to be next to each other. And very quickly, this self-repelling matter decays. So it can't stay in its state for a very long time, so it decays, and when it decays, it forms hot radiation and ordinary matter. And this was that radiation that is considered to be the fireball of the hot Big Bang. And this is where we get that energy, that radiation. So this was kind of the theory, cosmic inflation theory, that Alan Guth created. But what does that help solve? So right now, if this were correct, if cosmic inflation, if this was right, and if everything expanded as we expect, then the universe would be completely smooth. So what it would mean is that matter would distribute evenly. Because if all of this self-repelling matter does not want to be next to each other, then they want to kind of equally space out. And they want to all kind of be as far apart as from each other as they possibly could. So that's what we would expect to see. But here's the problem. If this were the case, if it was this self-repelling matter, we shouldn't see any of this matter kind of clumped up together. But that's not true, because we do have clumps of matter, which are called galaxies. So here, Stephen Hawking and Gary Gibbons had earlier proposed that if we have this inflating universe, an expanding universe, that there would be slight thermal fluctuations in this expansion, that it wouldn't be a smooth universe. And that as the universe expands and as it's blown up, this would be kind of exasperated. We would see it more. And so in 1982, the team here, Stephen Hawking and Gary Gibbons, suggested that if we could find these fluctuations, this would point to, this might provide the means for how these galaxies would be created, because these little thermal fluctuations would be where we would have more matter to create these galaxies. However, at this time, like kind of everything throughout this history of the Big Bang, we didn't really have the technology to really be able to observe this evidence. So thermal fluctuations was only a theory at this time, but we couldn't really actually prove that they existed and were a possible answer. However, in June of 2001, NASA launched a satellite called MAP. Here's a digital representation of this. So MAP stands for Microwave Anisotropy Probe. And the goal of this satellite was to make a detailed survey of that cosmic microwave radiation. So over this time, once it was suggested that this background microwave radiation would exist from Gamow, everyone was trying to say, well, how can we see it? How can we observe it? How can we measure it? We got that idea. We got the noise from the Arno and Penzias. We got the noise from it, but we really still couldn't really directly measure it, kind of picture it. And so that's what NASA was trying to do with this satellite, to be able to throw it out into the universe and see into space and see if we could kind of map out this microwave radiation and see if we can have some evidence for the birth of the universe. And so this is what they were trying to do. And they were successful, being able to actually map out and take a picture. And this is considered kind of the earliest view of the universe. It shows what it would have looked like energy-wise 13 billion years ago. So this pattern shows the microwave radiation that was produced by the Big Bang that's surrounding us. That radiation that I talked about that would be all around us, that would be very small. We couldn't really, it wouldn't affect us like, cooking a pizza kind of microwave thing, but it would be present and we would be able to observe it. And this is the same thing that we noticed in that background noise. And so this is the radiation. And as you see, if the cosmic inflation theory was correct in the sense of it being smooth, we wouldn't see thermal ripples. But Hawking and Gibbons suggested, based on their idea, that there would be these thermal ripples. And you can see that it's not smooth. You can see parts that are red or orange, and this is where those thermal ripples are. And based on their type and their size, they actually correspond to where we see galaxies today. And so, like we said, if they were to clump up, that would be a galaxy. And that's what they were predicting, that these thermal ripples would be places where those galaxies would form. And that's what we see. And that's how this observation was able to kind of confirm that theory. But however, we still wanted to know what came before. So we have the Big Bang. We kind of understand the process of, okay, what happened after, the initial bang and what happens after that. But people still wanted to understand, well, okay, well, what came before the Big Bang? What initiated the Big Bang? Because the self-repelling matter explanation, was defeated by Stephen Hawking and said it wouldn't be that way because then it wouldn't have clumps. So then what is the explanation? What is the thing that started that? Well, Stephen Hawking believed that the universe was spontaneously created out of absolutely nothing. And the way that he kind of describes it is if you think about boiling water. So if you have boiling water, there's going to be kind of little bubbles of steam. And so these little bubbles that kind of pop up would be kind of like universes. So tiny universes will spontaneously appear out of nothing, but most of them will collapse to nothing. So some of them will pop up and kind of pop out of the water. Some will just go back down. And then a few will continue to expand and form galaxies and stars, and in some people's hypothesis, even human beings. But let's look at this a little bit deeper, exactly what he means by these, little universes popping up. What was his explanation for this? So his explanation for this was using a quantum vacuum. So a quantum vacuum is a sea of fluctuating energy. So that's kind of this idea of the boiling water. But it has rich physical structure and it is described by physical laws. So it is something that we can describe that it's kind of in our box of natural laws and natural understanding. And that things can materialize out of the vacuum and then vanish back into it. So like this bubble idea. Theoretically, from vacuum fluctuations, it can cause anything to pop into existence. So based on just the theory, it's not just universes. We could have a dog, we could have a house, we could have a planet. Theoretically, anything could pop into existence by means of these vacuum fluctuations. Now let's think simply. So let's think about maybe just a pair of subatomic particles, because this would be the most likely because it's the simplest. What would that be? So even though they're the most likely, they would also only last a very brief amount of time. And from this theory, when this was proposed, they didn't propose actual subatomic particles to be able to exist. They actually only called them virtual particles. So even though this is a theory, they weren't able to determine that real physical subatomic particles could exist from this vacuum. Mathematically, they were only able to support these virtual particles. So right now, it's only really a theoretical construct. And then if we build up into bigger things, for example, a molecule, then it's even less likely, less probable that this would be something that would pop out and then actually be able to continue to exist. It would be able to pop, but then it would just go back. However, in 1973, Edwin Tyron suggested maybe that this was the precursor for the Big Bang. And so he's the one that kind of tied in this vacuum, quantum vacuum, with the Big Bang. But right now, it's not really a widely accepted or complete explanation in modern cosmology for the Big Bang. Like I said, because it's very unlikely for a molecule to be able to be produced or even larger things. And the subatomic particles that were able to were virtual particles. Now, vacuum fluctuations are a well-established concept in modern physics, but isn't something that is strongly connected with an explanation for the Big Bang. But even if we were to accept this as an explanation for the Big Bang, the quantum vacuum isn't nothing. It is still something. So as this being an explanation for creation out of nothing still leaves us wanting more, because the question is, well, if the particles are coming from the vacuum, the quantum vacuum, then where does the quantum vacuum come from? Where is this energy, this sea of fluctuating energy? Where did that come from? So we're still kind of left with trying to figure out, well, what started the Big Bang? What started this? If it was the quantum vacuum, then what started the quantum vacuum? So that's where science is at right now, of saying, okay, we've got to this one point and they're still trying to figure out, well, what comes before that and what comes before that. And there's been lots of different explanations, and all of the explanations so far fit into one of two camps. Either one, The explanation itself requires something to start it. So kind of like this quantum vacuum, it is an explanation, but then something needed to start it. It needed to have a cause. Or second, it is something that can exist and can be an explanation for the first cause, but only if it is using virtual or it might use imaginary numbers, something that is mathematically accurate, but isn't able to move into the observable real world. So it's only a theoretical concept, not something that is actual, something that we can expect would happen in our natural laws. So just to kind of summarize where we're at with our understanding of the Big Bang and our universe. So the universe is thought to be around 13.7 billion years old, has an uncertainty of 200 million years, which that might sound like a lot. 200 million, that's a lot of years. But in 13.7 billion, it's actually pretty small. In the first second after the universe began, the surrounding temperature was around 10 billion degrees Fahrenheit or 5.6 billion degrees Celsius, depending on your preferred system for measurement. And initially, there was no light. So until after about 380,000 years after the Big Bang did we have light, because photons didn't exist. So when we had the first initial Big Bang, we had neutrons, electrons, and protons, but we didn't have photons. So not until later did we actually have what's considered early light. And this is actually considered called afterglow. And this is the result of that cosmic microwave background, that radiation. And I have a picture on the next slide that will help as well. And it is believed that only 5% of the universe is actually made up of matter, of planets, stars, galaxies, and the rest is just empty space. Just to kind of give you an idea of the proportion of matter to the entire universe. So here is just a picture of kind of the idea of the expansion of the universe. So at the beginning, if we assume that right now the most common explanation is the quantum fluctuations. So quantum fluctuations initiated the Big Bang. We have that initial inflation that happened very quickly. Then around 400,000 years later, approximately 380,000 years, we get that afterglow from that cosmic microwave background radiation. Then as things are starting to cool and settle down, then that's when we get the expansion. We start to see some of the smaller elements to be formed. And then later on, we're starting to get our first stars, and that's where we're going to start having light. So we do have a little period considered the dark ages then. Get our first stars, about 400 million years. And then as the universe continues to expand, we get galaxies and planets and etc. So that is my talk on the Big Bang. Here are some references for you, depending on if you would rather read something or watch a video. Just a few pieces of background information for you.